Alright, hello everyone from Math 2000 Linear Algebra. This is Professor Wenson here again with a video on your ZyBooks Section 4.5 titled Cramer's Rule. Alright, now this is a particular procedure. Alright, Cramer's Rule is a procedure for using determinants to find solutions to square systems of linear equations. Now when I say a square system, that means the number of variables is the same as the number of equations, right? When you write it as a matrix equation, the coefficient matrix will be a square matrix. And of course, this only will apply, right? This Cramer's rule is very specific. It will only be able to be used if that square coefficient matrix is invertible, right? If its determinant is not 0. All right, so let's get into it. So Cramer's rule. So again, you can read the summary. Got the objectives here. Okay, so Cramer's rule. Right? Determinants can be used to solve a system of linear equations with n equations and n variables and unknowns. Right? Same number of equations as unknowns. Cramer's rule is a formula that uses the determinant of the coefficient matrix and a matrix formed by replacing the ith column of the coefficient matrix by the constant matrix B, right? That constant matrix on the other side of the equal sign. All right, so here it is, Cramer's rule. So let A be the coefficient matrix of a system of linear equations with n equations and n unknowns, right? So A will be a square matrix, an n by n matrix. And let, matrix B vector, column vector B be an Rn. That just means it has, n components, and, it's an n by 1 matrix. Be the constant matrix. So each component in the solution, right, x equals, x1 to xn, right, the solution vector. The solution to a times x equals b, I think they should have mentioned that. The solution to a times x equals b. Each component will be given by the following. So the ith component, right, so xi, will be the determinant of a sub I, matrix a sub I, divided by the determinant of the coefficient matrix. So you see why the coefficient matrix has to be invertible here, because you can't divide by 0, right? If a wasn't invertible, then the determinant of a would be 0, and you couldn't do this. Right? So a has to be invertible, has to have a non-zero determinant in order for this to apply. Right? So x1 will be the determinant of a1 divided by the determinant of a, x2 will be the determinant of a2 divided by the determinant of a, and so on. Where these matrices, these AIs, these AI matrices, AI is the matrix formed by replacing the ith column of matrix A by the constant matrix B. Right. Now, you've already seen how to solve systems of matrices with row operations, using Gaussian elimination with back substitution or Gauss-Jordan elimination. Right? You've seen how to solve systems already. This is just another method to solve a very particular kind of system, right? A square system with an invertible coefficient matrix, right? Very specific. So you can't always use this. You can always do Gauss-Jordan elimination or Gaussian elimination with back substitution. You can always do that stuff. That's always able to be done to solve a system. But this is, again, just one very specific use. All right, so I take you through an example there. I will just show you this 2x2 system, this 2-variable, 2-equation system, how to use Cramer's rule on a piece of paper. Okay, so here's a 2-equation, 2-variable system, a square system of linear equations. It's already set up the way I want it, where all the variables are on one side, constants on the other side of the equal signs, and like terms are in line with each other. Now, like I said, you don't have to solve this using Cramer's rule. Right? You can apply elimination, substitution, you do Gaussian elimination, Gauss-Jordan elimination, whatever. Right? You've seen other ways to solve systems. But I want to show you Cramer's rule though, just to give you another opportunity, another option. Right? So as a matrix equation, right, I'm going to write this as a matrix equation. So we have the coefficient matrix, with the coefficients of x1 down the first column, coefficients of x2 down the second column, multiplied by our variable matrix, right, with x1 and x2 in it. And this is equal to our constant matrix, our constant column, with the entries 15 and 13. Okay, so here we have the A, that's our coefficient matrix A, times the x, right, the vector x, that's our variable matrix, equals our constant matrix, and it's a column vector B. Right. So first I'm going to find the determinant of the coefficient matrix. What's the determinant of A? Right. Now it's a simple 2 by 2. Right. So negative 36 minus 6. Right. This would be negative 42. Right. Negative 36 minus 6. This is not 0. Right. This is not 0, meaning that A is invertible. But more importantly for this section, if our coefficient matrix is invertible, that means we can use Cramer's rule to solve the system. Okay. Again, if the determinant was 0, there wouldn't be any need to use Cramer's rule. All right. You would have to do it. Try to find the solutions to the system using Gaussian elimination or Gauss-Jordan elimination. Okay, so there's a determinant of the coefficient matrix. Now, I'm going to form those matrices, A1 and A2. Right? So A1, this A sub 1, this matrix is just the coefficient matrix. Okay, it's the coefficient matrix, but I'm replacing the first column with the constant column over here. So instead of the first column being 12 and 2, the first column is 15, 13. Right, that's why I got that in the pink over here. Right. And then the rest of the coefficient matrix stays the same. All I did was replace the first column. So the second column is still 3, negative 3. Right. And A2, right, there are two variables here, so I'm going to be finding two of these matrices. A2, right, A2 is the same thing. It's the coefficient matrix, but with the second column replaced by the constant column here, 15, 13. So again, 2 by 2 matrix where the first column is still 12 and 2, and the second column is replaced. So the 3, negative 3 is replaced with the 15, 13. Okay. All right, so now I find the determinants of these, right, which again, very simple. These are just 2 by 2 matrices. All right, so what is the determinant of A1. So that'd be a negative 45 minus 39. So that's negative 45 minus 39. That'd be negative 84. Right, that's the determinant of A1. And the determinant of A2 is the determinant of this matrix. All right. So 12 times 13 is 156 minus 30. 156 minus 30, 126. All right, and now that I have all these determinants, I can find the solutions of the system, right? So we can now find the components of the solution, the x1 and x2. We can find the components of the solution to this system. So x1 is going to be the determinant of A1 divided by the determinant of A. Right? The denominator in all of these is the determinant of the coefficient matrix. All right, so the determinant of A1 we saw was negative 84 divided by the determinant of A, the coefficient matrix, was negative 42. And negative 84 divided by negative 42 is positive 2. Right? So the x1 component of the solution to this system is 2. And the same thing for x2. Right? The x2 component of the solution will be the determinant of A2 divided by the determinant of A. All right, now the determinant of A2 we saw was 126 divided by the determinant of A again is negative 42. And 126 divided by negative 42 is negative 3. All right, and then I can put these together and we get the solution of our system. Right? So the solution of this system, I'll write it as a column matrix, is x1, x2 equals, I replace x1 with 2 and x2 with negative 3. And there we go. Now let's check this, and I'm going to double check this, of course. Always check your solutions. Replace x1 with 2 and x2 with negative 3. All right, so 12 times 2 is 24. 3 times negative 3 is negative 9. 24 minus 9, plus negative 9 is 15. That's true. And then 2 times 2 is 4. Negative 3 times negative 3 is positive 9. 4 plus 9 is 13. Works. Okay, so again, if your coefficient matrix is invertible, if the determinant's not 0, then you can go and do this. This is called Cramer's rule, what I just did here for this two equation, two variable system. Right. Now again, this is just an alternate method. You could have just done elimination, right? Gauss-Jordan elimination, which would have probably been easier. I will say in most cases it's easier to do the Gaussian elimination with back substitution or Gauss-Jordan elimination. This method here, Cramer's rule, especially with larger systems, can take quite a while. As we'll see with my next example. My next example will be a 3-equation, 3-variable system, but we'll get to that in a second. All right. So they go through here and do the same stuff, right? 2, negative 3. All right, so I leave it to you to do this one. Okay, write this as a matrix equation with a coefficient matrix times a variable column matrix equals a constant column matrix. And then what's the determinant of the coefficient matrix? Now remember, A1 is that coefficient matrix where the first column is replaced by negative 11, negative 13. And A2 is the coefficient matrix where the second column is replaced by negative 11, negative 13. Find those determinants and then divide things to get x1, the x1 component of the solution and x2 component of the solution. All right, so let me do this example. All right, so I'm going to do this example on paper. Use Cramer's rule to solve a system with 3 equations and 3 unknowns. Okay, so I've written this system and wrote it as a matrix equation. Again, this is in the form A times the variable column matrix, the column vector x equals the column vector column matrix of constants, called B. All right, so first, if I'm going to use Cramer's rule, I'm going to try to use it. I got this square, again, a square system, square coefficient matrix. First, I determine if I can even use Cramer's rule. Right. So again, probably easier to do Gauss-Jordan elimination, but let's use Cramer's rule like we're in this section. So let me find the determinant of A. Now I'm going to do a cofactor expansion. I'm going to go down the first, I'll go down the first row. I got 1 times the minor, negative 2, 1, 3, negative 2. And then, plus 1, but then the minor will, the cofactor will be the opposite of the minor because I'm in an odd position. Get rid of the first row, second column. You got the minor, the determinant of 3, 1, 1, negative 2. And then plus negative 1, so minus 1 times its minor. Right, the cofactor would be equal to the minor because I'm in an even position. 3, negative 2, 1, 3. Alright, so this is negative 4 minus 3, that's negative 7, times 1. This is negative 6 minus 1, it's negative 7, but then times negative 1 would be plus 7. So right now we have 0. And then here we have 9 minus negative 2, which would be 9 plus 2, that'd be 11, so minus 11. So this is negative 11. Alright, so this is not 0, good, right? But negative 11, right? The determinant of the coefficient matrix is negative 11. Oop, no it's not. No it's not. Sorry, I just saw an error. This is not negative 7, I apologize. This is positive 4 minus 3, that's 1. Okay. So not negative 7. My apologies. And let me double check the other ones. Negative 6 minus 1. This is negative 7, and then plus 7. Okay, good. All right, and then let's see, that one's that's correct. And then 9 minus negative 2 is 11. Minus 11. Okay. So this is 8 minus 11. All right, so the determinant's negative 3. My apologies. But still not 0, right? That's still good. All right, so the determinant of my coefficient matrix is negative 3. All right. Okay, and if you want to use a calculator to verify that, why not? All right, now I'm going to form those. Now there are 3 variables, right? So I'm going to form 3 new matrices using this constant column and replacing columns in the coefficient matrix. Right, so I'll make sure the coefficient matrix is still visible. And let's form the first matrix, A1. Okay, now A1, remember, is the coefficient matrix, but where the first column is replaced by the constant column. Okay, so that means the first column is no longer 1, 3, 1. It's going to be 6, negative 5, 14. And then the other 2 columns are the same. 1, negative 2, 3, and negative 1, 1, negative 2. Alright, so let me just go through and find the determinant of this matrix right now. So I'm going to pause it and just come back when I'm done with that. Okay, so I did the cofactor expansion again across the top row, and I got negative 3. All right, I got a determinant of negative 3 for A1. All right, now let me write up A2. So again, there's the coefficient matrix, the original. All right, so A2 again is that coefficient matrix, but where the second column is now replaced by this constant column. So the first column is the same, 1, 3, 1, but now the second column is that 6, -5, 14. All right, and then the third column is the same as the original, -1, 1, -2. All right, and again, I'm going to pause it and write out the determinant with some cofactor expansion here, and I'll just go across the top row again. So the determinant of A2, I'll come back when I have that. All right, so I went through and did a cofactor expansion across the first row here, and I got -9 as the determinant of A2. All right, and then one last one. All right, so again, here's the coefficient matrix up top here, and I'm going to create the third matrix, A3. So A3, now remember this is just the coefficient matrix with that third column replaced by the constant column 6, -5, 4. So the first two columns stay the same, 1, 3, 1, 1, -2, 3. And the third column, 6, -5, 14. All right, and now I'm going to find the determinant of A3. And again, I'm just going to go across the top row, do cofactor expansion, and I'll pop this back up when I have it. All right, so doing cofactor expansion across the top row again, I got the determinant of A3 is 6. All right. So now finally I can find the components of the solution and then state the solution. All right, so the components of the solution, we have x1. Again, x1 is the determinant of A1 divided by the determinant of the coefficient matrix A. Now the determinant of A1 we saw was -3 divided by, and the determinant of the coefficient matrix was also -3, after I caught that mistake of mine. And this is just, this is nice. This is +1. +1. Okay. Then x2. x2, same concept. It's the determinant of A2 divided by the determinant of A. Now A2 had a determinant of -9. All right, so this is -9 divided by, and then -3 again. So x2 is +3. All right, and then finally x3 is the determinant of A3 divided by the determinant of A. All right, the determinant of A3 we just saw was +6 divided by -3 again. This is -2. All right, so the solution of this system. All right, so the solution of this system is 1, 3, -2. So here's the system again. All right, so the solution, I'll write it as a column matrix, x1, x2, x3 equals 1, 3, -2. And you can verify this by plugging in, 1 for x1, 3 for x2, and -2 for the x3s. And yeah, it does work. It does work. Just glancing at it, doing some mental math here. All right, wonderful. All right, so going back, 1, 3, -2. Right. So you're asked to do that here. Okay, so write this system as a nice matrix equation. A times some variable matrix x equals the constant column matrix 7, 3, 1. What's the determinant of the coefficient matrix? What's the determinant of that matrix when I replace the first column by 7, 3, 1? When I replace the second column by 7, 3, 1, and when I replace the third column by 7, 3, 1, and then find the components x1, x2, and x3 of the solution. And then you're doing the exact same thing here. Now this one, see the first problem here is just what would be the matrix A1? So it's just replace the coefficient matrix, replace the first column with 0 and 1. The second column stays the same, -5 and -3, and that's all this first one is. All right, let's see. I'll just go through the next level, and pretty sure at some point they have you solving a system with Cramer's rule. So the next level, okay, the next level is similar. Just what would be the matrix A3? So you replace, take the coefficient matrix here, replace the third column with the 3, 2, 1. Yeah, let's look at the last level. Yeah, so this one's actually find just one component of the solution. What's x3? So there's no need to find all the solutions, all the components, right? Just find x3. So you would find the determinant of the coefficient matrix, and then that coefficient matrix with the third column replaced with 16, -26, 27. And I would recommend using your calculator after a while, right? Because some of these numbers are getting larger. So hopefully you remember how to find determinants on your calculator. Remember how you can, here's a calculator. TI 83, 84 are pretty similar. Remember, you can enter a matrix, go second matrix, and then over to edit and make matrices. And then in the math menu, right, there's DET right there. You can use that, find the determinant of, and then go to names and plug in your matrix right on the main calculation screen. So, and you've seen me do that before in previous videos, where I use the calculator to find determinants. So it might be a little faster, a little quicker to do it with the calculator, especially because there seems to be a bunch of these. All right, now the final part of this section is again still using Cramer's rule, but now instead of the solution to a system being a bunch of numbers, being constants, the solution will be functions. Now if you've taken linear differential equations, or you're about to, something you're going to learn about are things called Laplace transforms. I'll read this here to you. A Laplace transform reduces a system of linear differential equations by transforming equations containing derivatives with respect to a certain variable into a system of linear equations in terms of a parameter that can be solved using algebraic methods like elimination, Gauss-Jordan elimination, or Cramer's rule. So they go through an example here where you're trying to solve for x of s and y of s, these functions of s, this parameter s. All right, so you set it up. I'll show you how it's done with this example, and then you're asked to do the same in a different activity. All right. So here you say solve the system for these. So now the solutions of a system are going to be a function of some parameter, a function of some variable, as opposed to just numbers. But the procedure doesn't change. All right, the procedure doesn't change, and I'll show you on some paper. Okay, so here's a system of equations where what you're trying to solve for this time are not just single variables, but entire functions. You're trying to solve for x of s and y of s, right? You're trying to figure out what these functions need to be, these functions of s, this parameter s, so that this system will be true. Both equations will be satisfied. So I want to replace x of s with some expression, and I want to replace y of s with some expression so that both of these are true. All right, so just like earlier, again, it's just going to look a little crazier because there's going to be more letters, but it's the same procedure as earlier with Cramer's rule. You can write it as a matrix equation, where you have your coefficient matrix, which down the first column, the coefficients of this x function. So we have s, right, s, and then -1. And then down the second column, the coefficients of this y function, y of s. So we have +1 up here times y of s, And then, S, positive S down here times y of s. So there's the coefficient matrix times the function matrix, or the variable matrix with, x of s and y of s, what I'm trying to find, what I'm trying to solve for, equals, and then over here, a, constant matrix, but, it will involve variables, right, parameter s, 1 over s plus 1 for the first entry, and then this s plus 4 over s plus 1 for the second entry, because if you replace s with some value, these are going to be constants if you s represents some real number. So we have our matrix A, this matrix of functions, like a vector x, and then over here, again, if s represents some real number, so this if s represents a real number, this is a matrix of constants technically, B, vector B. All right, so again, I want to find expressions for x of s and y of s that make both equations true. So let's this is a square system. We have a square coefficient matrix, so I can apply Cramer's rule. So what's the determinant of A? That'd be s times s minus 1 times negative 1. So s squared plus 1. All right, then I've got these two unknowns I'm looking for, these two unknown functions, x of s, y of s. So I'm going to create these two matrices, A1. A1 is again the coefficient matrix, but the first column is replaced by the matrix of, the constant matrix B over here. So the first column has entries 1 over s plus 1 and s plus 4 over s plus 1. And the second column doesn't change, right? You still have 1 and s. Now, what's the determinant of A1? Nice 2 by 2. It would be, s over s plus 1, I want to multiply these two, minus, and then 1 times this would be minus s plus 4 over s plus 1. Now this is, you're subtracting that whole numerator, right? So it's s minus the quantity s plus 4 over s plus 1. Now they both have a denominator of s plus 1, right? So that'll be the denominator of the resulting difference. And then s minus the quantity s plus 4 will be negative 4. Or I would distribute the minus, and s minus s is gone. Right, so there's the determinant of A1. Right. And I do the same thing for A2, right? There are two unknown functions I'm trying to find. So I need two of these matrices. So again, it's the same as the coefficient matrix here. So the first column is the same this time, but the second column is replaced by this B here, this 1 over s plus 1 and s plus 4 over s plus 1. Okay. And then we find the determinant of this matrix, right? The determinant of A2. Again, now multiplying these, you have s times s plus 4 in the numerator, s plus 1 in the denominator. Then minus the product of these two, but this is negative this, negative 1 times 1 over s plus 1, so minus, that'd be positive 1 over s plus 1. And these have the same denominator. Now this is just s squared plus 4s plus 1, so we have s squared plus 4s plus 1 over s plus 1. And there you go. Right. So now I've got these determinants, right? Determinant of A1, determinant of A2. And we find those components of the solution to this system. So that x of s that I'm looking for would be the determinant of a1 divided by the determinant of a. So the determinant of a1 was this negative 4 over s plus 1. And then dividing this by, the determinant of a we saw earlier was s squared plus 1, right? Divided by s squared plus 1. Well, that's just going to put s squared plus 1 in the denominator with s plus 1. So this is negative 4 over, s plus 1 times s squared plus 1. So there's the expression for x of s that I need. And we'll check this, we'll verify this in a minute. And y of s, the other unknown, that other unknown function of s, will be the determinant of a2 divided by the determinant of a. Now the determinant of a2 was this thing. Right, so s squared plus 4s plus 1 divided by s plus 1. Right, that's the numerator. And then divided by s squared plus 1 again. And that's just going to put s squared plus 1 in the denominator with s plus 1. So this is s squared plus 4s plus 1 divided by, then the quantity s plus 1 times the other factor s squared plus 1. And there you go. These two expressions here for x of s and y of s make up the solution of this crazy system that we saw in the beginning. So let me check. Let me show you. I'm going to replace x of s with this expression here and the y of s's with this expression. And we're going to see that indeed both of these expressions, both of these equations will be true statements. Right, these are the solutions of this system. Right. So I'm going to keep these off to the side here and we'll do our replacement. So let's check. Let's verify that these are indeed the solutions of this. This is indeed the solution of the system. So we have s times the x of s I said was negative 4 over s plus 1 times s squared plus 1. Right, that was what I said I got for x of s. Plus, and then the y of s, we got s squared plus 4s plus 1 over the s plus 1 times s squared plus 1. Now, is this equal to this 1 over s plus 1 on the other side? Because if it is, then it's true. Well, let's see. This would just be negative 4s over s plus 1 times s squared plus 1 plus, and then you still have this over here, the y of s, s squared plus 4s plus 1 divided by s plus 1 times s squared plus 1. These have a common denominator, so I can put the numerators together. So we get that same denominator, right? Common denominator here in the sum. And then what happens when I put these together? You see negative 4s plus positive 4s, so the s terms are gone, and I'd be left with s squared plus 1. And then look, those cancel, s squared plus 1 and s squared plus 1, and I'm left with 1 over s plus 1, exactly what the right side is. So check on that. The first equation is satisfied. All right, and then I'll do the same for the second equation. So for the, just do a separate paper. All right, so for the second equation, we have the opposite of x of s, which was the negative 4 over s plus 1 times s squared plus 1. Right. Plus s times the y of s. Now the y of s we found was s squared plus 4s plus 1 divided by then the s plus 1 times s squared plus 1 again. Now, hopefully, when I'm done simplifying this, I end up with s plus 4 over s plus 1, right? The right side of this second equation. Let's see. Well, the opposite of this would be positive 4 over s plus 1 times s squared plus 1 plus, and then when I multiply the numerator of this by s, I'd have s cubed plus 4s squared plus s divided by s plus 1 times s squared plus 1. Alright, now these have the same denominator. I can put them together. And then adding the numerators together, we get s cubed plus 4s squared plus s plus 4 divided by s plus 1 times s squared plus 1. Now the numerator can be factored by grouping. You might have heard of that before from algebra class. I take the left half, pull the s squared out. You'd have s squared times s plus 4. Take the right half. They have a common factor of 1 times s plus 4. Then pull the s plus 4 out. So you have s plus 4. And then if you pull the s plus 4 out, what you're left with would be s squared plus 1. That's the numerator factored. And then you have the denominator s plus 1 times s squared plus 1. And oh look, there's the common factor of s squared plus 1 again. Those cancel. And I have s plus 4 left in the numerator, s plus 1 left in the denominator. Hey, that is the right side of this. This equation is indeed satisfied by that x of s and that y of s, right? These two things I found earlier. So this is the solution of that system. This for x of s and this for y of s. It works. It makes both equations satisfied. Both equations are true. All right, so see, Cramer's rule still applies, even if your system, the solution of your system is going to be, functions instead of just numbers. The Cramer's rule can still be applied if the amount of unknown functions is the same as the number of equations, right? It's a square system. So you got another example here, and again, I'll leave this to you. So again, you're going to make a, so you have s plus 2 and negative 2 down the first column of the coefficient matrix, matrix A, and then negative 2 and s plus 5 down the second column, and then find the determinant of that. Now that would be s squared, let's see, that'd be s squared plus 7s plus 10 minus 4, so s squared plus 7s plus 6. So I'll just give you the first one. This would be the determinant of the coefficient matrix, s squared plus 7x plus 6. Right. Which can factor to s plus 6 times s plus 1. You might need that later. All right, then replace one of the columns, the first column with this 1 over s squared plus 1 and 0. Find the determinant of a1. Replace the second column with this. Find the determinant of a2, and then do some divisions. Find x of s, y of s, and all the options should be here. All right, and then you have your additional exercises. All right, so again, some of these are in your assignment, assignment 7. Some are not. I would still recommend doing all of them. All right, just to get more practice, more familiarity with the material, get better at it. And then you can check. You can verify your work by checking the solutions after. Right? Please, look at the solutions after you've worked on it, after you tried to figure it out on your own. Because you're not going to learn anything, if you just copy solutions. So that's it for section 4.5, and that's it for chapter 4 as well. Right? The chapter on determinants. So hopefully this video helps guide you through section 4.5 when you work on it on your own. And of course, if you have any questions, send them my way, let me know. And thank you very much for watching.